Hi guys, we've been talking about thermodynamics and we had talked about enthalpy and entropy. These are the two driving forces that determine if a reaction is going to be thermodynamically favorable or spontaneous at given a certain condition. And we had also talked about delta G, which is Gibbs free energy. It's a made-up thermodynamic variable that combines enthalpy and entropy together so that we can tell whether the reaction is spontaneous or not. Delta G naught is what we've been calculating for the most part, and we have been using these tables here to calculate whether it's delta H or delta S or delta G. And remember, these are at standard conditions. We know that by the little degree sign there. It means delta G naught, which is at standard conditions, which means 25 Celsius, 1 atm of pressure, and also 1 molar solutions. So what if you're not at standard conditions? What if you're at a different temperature? Or what if you're at a different pressure? Let's say it's not 1 atm. Well, that's going to affect gaseous species, right? Because the entropy would change if the pressure changed. So to relate between delta G, which is at any conditions, any temperature, any pressure, versus delta G naught, which is at standard conditions, you can use this equation. Delta G is equal to delta G naught, so at standard conditions, plus RT ln of Q. R is the ideal gas constant. It's 8.31 joules per mole Kelvin, or if you're using kilojoules, it's 0.00831 kilojoules per mole Kelvin. Remember that a joule is equal to a kPa times liters, so that's the R value that we used when it was kPa times liters per mole Kelvin, because a joule is a kPa times liter. And then T, of course, is the temperature in Kelvin. And then ln of Q. Q, if you remember, is the reaction quotient, which is either the concentration or the pressures of products over reactants raised to the power of their coefficients. So again, we can express Q in terms of concentrations, or we can express it in terms of partial pressures if you are looking at a reaction where there are gaseous species. So we can relate, again, delta G at any given conditions to the delta G naught by saying that it's delta G naught plus RT ln of Q. So let's look at this problem here where we have decomposition of water and we're asked to calculate delta G at 700 Kelvin. We're given the partial pressures and we are asked, is this spontaneous, and which way will it proceed? So since we are trying to find delta G at 700 Kelvin, we're going to say delta G is equal to delta G naught plus RT ln of Q. And we're going to start with delta G naught. We're not given that value, so we're going to calculate it. So delta G naught, I can use my tables, is products minus reactants. So my products, I have 2 moles of H2. It's 0 kilojoules per mole because it's an element in its natural state. Then I have 1 mole of O2. It's also 0 because it's an element in its natural state. So those are my products. Minus the reactants, I have 2 moles of H2O. And my value here is negative 228. 0.57 kilojoules per mole. And so altogether my delta G naught is 457.1 kilojoules per mole. Okay, so I got delta G naught, I apologize, plus then we have R is a constant, we got that. T is the temperature, we have that. ln of Q, we don't know what Q is, so let's calculate Q on this side here. So Q is products over reactants raised to the power of their coefficients. We're given pressure, so we're going to express it in terms of pressure. So it is the partial pressure of the H2 squared times the partial pressure of the O2 over the partial pressure of the H2O squared. So the partial pressure of the H2 is given to us as 0.0002 atm. We're going to square that. O2 is 0.0001 atm. and H2O is 0.85 ATM, and we're gonna square that as well. So my Q here is 5.54 times 10 to the negative 12th, really small number. So now that we have all the pieces, let's put it all together. So delta G is going to be delta G naught, which we got to be 457.1 kilojoules per mole, plus R. Since we're using kilojoules, we're going to use this value here, 0.00831 kilojoules per mole Kelvin. T is 700 Kelvin, and then ln of Q, so ln of 5.54 times 10 to the negative 12. Go ahead and punch that into your calculator. You get delta G is equal to positive 306.3 kilojoules per mole. So that's our delta G. So what does that mean? Well, if delta G is positive, that means it's not spontaneous, not thermodynamically favorable. So what does that also mean? That means it's not product favored, it's actually reactant favored. And so if it's reactant favored, that means that it's proceeding to the left to make reactants because it's reactant favored. And so my reaction is proceeding left. And so if my delta G is positive, it's not spontaneous, it's reactant favored, and it's proceeding to the left to make those reactants because it's reactant favored. Okay, let's look at another one. So here we want to determine the direction of the reaction. We're given initial pressures for my gases here, and that's all it asks. Determine the direction of the reaction. Well, to determine that, we want to calculate delta G. So we're going to say delta G at 700 Kelvin is going to be delta G naught at standard conditions plus RT ln of Q. So delta G is given to us. It is negative 92 kilojoules plus R, since we're using kilojoules, we're going to use 0.00831 kilojoules per mole Kelvin. T is 700 Kelvin again. And then ln of Q, we don't have Q, so let's calculate Q on this side here. So Q is going to be products of a reactant, so the partial pressure of the H2O over the partial pressure of the CO times the partial pressure of the H2. We don't include the solids, of course, in our pressures. So H2O, the value for that is 0.67 ATM over carbon monoxide is 0.23 ATM, and my H2 is 0.51 ATM. So when we calculate that, we get that Q is equal to 5.71. So we're going to go back, punch that in, 5.71. And so my delta G ends up being negative 81.9 kilojoules per mole. So what does that mean? Well, a negative delta G means it is spontaneous, thermodynamically favorable, or spontaneous, which means it's product favored. So what does product favored means? It means that it's proceeding to the right. The forward rate is faster than the reverse rate, right? To make more products because it's product favored. So it's going to go in the direction of the products. So this means that it's proceeding to the right. So if delta G is negative, it's spontaneous, thermodynamically favorable, product favored, so it's going to go towards the product, which is to the right. If delta G is positive, that means it's not spontaneous, and so that means that it's reactant favored, so it's going to go towards the reactant, which is to the left. So this is saying just that. So if delta G is equal to 0, well, that means that products minus reactants is equal to 0, right? Which means we're at equilibrium. So if delta G is 0, we're at equilibrium, which means the reaction quotient is equal to the equilibrium constant. Q is equal to K. System at equilibrium. Great. It's not proceeding to the left or to the right. It's at equilibrium. The forward and the reverse rate are equal to each other. If delta G is negative, it's less than 0. If it's negative, that means it's spontaneous. It's product favored. It's going to proceed to the right to make more products. Because if delta G is negative, that means that the products are lower in Gibbs free energy than the reactants. Therefore, you get a negative value, which means that Q, the products to reactant ratio, is too small compared to K. So the ratio of products to reactants right now is too small compared to what it is at equilibrium. Q is where you are right now, K is at equilibrium. And so if your delta G is negative, that means that the products are lower than what they should be. The ratio of products to reactants is lower than what it should be at equilibrium, and so that means it's product favored. It's going to keep going to the right to make more products. If delta G is positive, that means it's not spontaneous. It's reactant favored. It's going to go to the left to make more reactants. And that is because if this value is positive, that means that the Gibbs free energy of the products is higher than the reactants. And so Q right now is too high. The ratio of products to reactants is too high compared to what it should be at equilibrium. So the system proceeds to the left in order to reach equilibrium. One last concept here. We said that delta G is equal to delta G naught plus RT ln of Q. Well, at equilibrium, delta G we said is equal to 0. Also, at equilibrium, Q is equal to K. That's a capital K here. And so if I plug in 0 for delta G, because we're at equilibrium, and if I plug in K for Q, because we're at equilibrium, then at equilibrium, delta G naught is equal to negative RT ln of K. So that's another way to calculate delta G, or to calculate the equilibrium constant. So you can link between delta G and the equilibrium constant using this. So let's try this one here. It says given the reaction, we're using chromium oxide plus aluminum to yield aluminum oxide and chromium. It's a single replacement reaction. We want to calculate delta G naught and K at 298 Kelvin, which is standard conditions. So since I want delta G naught, I can use products minus reactants using my table. So let's see, delta G of the reaction would be, I have 1 mole of Al2O3. Value for that is negative 1,582.3 kilojoules per mole. I also have 2 moles of chromium. It's an element in its natural state, so 0 kilojoules per mole. Those are my products minus the reactants. I have 1 mole of Cr2O3. The value for that is negative 1,058 kilojoules per mole. It's a negative here. Plus 2 moles of aluminum. The value for that is 0 kilojoules per mole because it's an element in its natural state. So I get delta G naught for the reaction to equal negative 524 kilojoules per mole. And what does that tell us? This is spontaneous or product favored. So what do you expect for K then when you calculate K? Well, if it's product favored, then we would expect K to be higher than 1, right? So let's look at K. So we're going to use delta G naught is equal to negative RT ln of K. So negative 524 kilojoules per mole is equal to negative 0.00831 kilojoules per mole Kelvin times T, 298 Kelvin, ln of K, and we're going to solve for K. So natural log of K, if you take this number divided by this, gives you 211.6, and so to get K by itself you take e to that power, and so K is equal to 7.88 times 10 to the 91st. Whoa, very product favored. That's a huge number, right? That's almost a reaction that goes to completion as opposed to an equilibrium, right? So again, the more negative the value for delta G, the more spontaneous it is, the more product favored, the higher the value for K will be. The more positive delta G is, the less spontaneous it is, the less product favored, it's actually going to be reactant favored, and your K value will be small. It'll be smaller than 1. All right, that's it for the chapter. Have a great day, guys.